Right, in this course we're looking at NMR and we're going to do problem solving with NMR, but in many cases I will give you infrared spectra to provide additional clues when you're trying to solve a particular molecule. Now, you may be experts on IR, and if you know additional information about IR, that is fantastic. But the bare minimum that I need you to know is from IR is I need you to be able to find the OH in IR and a carbonyl in IR. Please look for these because that can give the required clue to solve a particular molecule using NMR. So please be aware that where the OH is, the OH band is very, very broad. So you can see here this particular compound, this infrared spectrum, includes an OH, but of course there's no carbonyl for this one. Here's a compound that has no OH, there's no broad OH in this particular compound, but there is a carbonyl. Please look for those two, as that will provide a little bit of extra information to help solve problems when you're working with NMR. So I'm not going to concentrate on IR, I really want to concentrate on NMR. Now, sometimes this is called degree of unsaturation, but double bond equivalence is a really useful tool to help you piece together what a compound is. Because if you have a look at a compound and you look at the carbons, the hydrogens, oxygens, and nitrogens, for example, you can calculate the double bond equivalence using this formula here. Now, what this gives is it gives a result. If you put in the number of carbons plus twice the number of carbons plus 2 minus the number of hydrogens and then of course plus the number of nitrogens and divided by 2, you find out how many double bonds there are in your molecule. Or rather, more accurately, you find out the number of double bonds or rings that you have in your compound. So just to give an example, if we have a look at C6H6, in this we have A is 6, and we have B is 6, and we have D is 0, and when you calculate 2 times 6 plus 2 minus 6 over 2, you end up with 4. The reason that the double bond equivalence is 4 for benzene is because you've got a ring that counts 1, and because you've got 1, 2, 3 double bonds. So double bond equivalence tells you the number of rings and or double bonds you have in a molecule. Just please, can I make you aware that if you've got a halogen or if you've got something that has a valence of 1, please include that. Add a chlorine. If you've got a chlorine, add it to your number of hydrogens to make this formula work. Essentially, this formula is working on atoms with a valence of 4, with a valence of 1, with a valence of 2, with a valence of 3. So please include that. Include halogens with hydrogens if you're calculating double bond equivalence. Okay, so please, just to see where we've got to at this point, remember we've got carbon 13 NMR, but we include multiplicity information from the protons that are attached to each carbon. Look for that. We cannot integrate, but we normally can see all of the carbons within a molecule. If we can't, we know there's some doubling up, so we've got to look very carefully for which signals are likely to be doubled up in the carbon spectrum. To solve problems in NMR, we can also have information from IR. At this stage I will not provide MS data. The two main structural features, at a bare minimum I want you to know, are the broad OH and the strong CO bands. If you know more about IR, that does help. Double bond equivalence is a really important tool. Learn that formula, be able to use it, because it determines the number of double bonds and rings present from the molecular formula. So if you propose a solution, you look at a spectra and you think a molecule might match, you can check that your double bond equivalence is correct. Please have that as an additional piece of information.